Welcome to G Fun Facts Online. Today we're diving deep into a technology that promises to reshape our world, quantum computing. We've all heard the buzz, the promise of machines that can solve problems impossible for even our mightiest supercomputers. But where are we, really? We're currently in what's called the Noisy Intermediate Scale Quantum Era, or NISQ for short. It's a stepping stone, a pioneering age where our machines are powerful, but also incredibly delicate and flawed. The biggest problem, the one word that defines this entire era, is noise. Now, this isn't the kind of noise you can hear. It's a far more subtle and destructive interference from the environment. The slightest vibration, a stray magnetic field, or a tiny change in temperature can corrupt the fragile quantum states of the computer's core components, the qubits. This corruption, known as decoherence, causes a qubit to lose its quantum magic, its ability to be both a 0 and a 1 at the same time, a property called superposition. When decoherence happens, errors creep into the calculation. So while we can now build machines with over 1,000 qubits, they are not the perfect, error-free computers we dream of. They are noisy, and that noise limits how many steps or operations a quantum calculation can have. To truly unlock the potential of quantum computing for things like discovering new drugs or creating revolutionary materials, we have to move beyond this noisy era. We need to build a new kind of quantum machine, one that isn't just bigger, but fundamentally better and more stable. This is the journey into the next frontier, the age of fault-tolerant quantum computing. At the heart of a quantum computer, you have the qubit. A classical computer bit is simple. It's either a 0 or a 1. A qubit, however, can be in a superposition of both 0 and 1 simultaneously. And qubits can be entangled, meaning their fates are linked no matter how far apart they are. This is where their incredible power comes from, but it's also the source of their greatest weakness: extreme fragility. This fragility leads to errors. Two main types of errors plague our current machines. The first is a bit flip, where a qubit unexpectedly flips from its 0 state to its 1 state, or vice versa. The second is a phase flip, a more subtle error that messes with the relationship between the 0 and 1 states within the superposition. In today's NISQ computers, which have anywhere from 50 to a few hundred qubits, fighting these errors is a constant battle. The operations we perform on these qubits, known as quantum gates, are pretty accurate, about 99.5% for a single qubit. But that small 0.5% error rate adds up incredibly fast. With an error rate like that, a quantum computer can only perform about 1,000 operations before the accumulated noise completely drowns out the actual signal, making the final result useless. This is the core challenge holding us back. It's why we can't yet run the truly complex, world-changing algorithms that might require millions or billions of operations. To get there, we need to solve the noise problem. This has sparked a global quest for the perfect qubit, one that's stable, scalable, and easy to control. While the superconducting qubits used by giants like Google and IBM have pushed the field forward, scientists are exploring fascinating alternatives. One of the most exciting are topological qubits. Instead of storing information in a single, localized particle, they encode it in the collective, braided properties of a group of particles. This makes them naturally resistant to local noise, a bit like how a knot in a rope is more stable than a single twist. If you disturb one part of the braid, the overall knot, the encoded information, remains intact. This could dramatically reduce error rates. Another major contender is the silicon spin qubit. These leverage the spin of a single electron trapped in a tiny semiconductor device, very similar to the transistors in the computer or phone you're using right now. The huge advantage here is that we could potentially use the existing, incredibly advanced semiconductor manufacturing industry to build them. The challenge has been protecting the electron's delicate spin state from electrical noise in the silicon. But recent advances using isotopically purified silicon are making these qubits much more stable. Then there's the world of light, with photonic qubits. These use single particles of light, photons, to carry quantum information. A huge benefit is that photons can travel long distances through fiber optic cables with very little decoherence, and they can operate at room temperature, unlike other qubits that need to be supercooled to near absolute zero. The main challenge is preventing photon loss, where a photon gets absorbed or scattered, which erases the qubit. But their potential for networking and room temperature operation makes them a very attractive option. Other designs, like trapped ion qubits, which hold individual atoms in electromagnetic fields and manipulate them with lasers, have already achieved some of the longest stability times and highest operational accuracies to date. It's likely that the future won't be a one-size-fits-all solution. We might see hybrid computers that use different types of qubits for different tasks, all integrated into one powerful machine. Each of these new architectures is a step beyond the noisy limitations of today, bringing us closer to a truly fault-tolerant quantum computer. But even with a more stable qubit, errors will still happen. Quantum mechanics is probabilistic by nature. This is where the quantum safety net comes in, quantum error correction, or QEC. This is arguably the biggest challenge of all. You see, in a classical computer, error correction is easy. You just make a few copies of a bit. If you have 3 bits that should all be a 1, and one of them flips to a 0, you can just take a majority vote and flip it back. But in the quantum world, there's a fundamental rule called the no-cloning theorem. It states that you cannot create an exact copy of an unknown quantum state. This forced researchers to come up with something far more clever. The solution is to use redundancy and entanglement. Instead of storing your information in one physical qubit, you distribute that single piece of quantum information across many physical qubits, entangling them in a very specific way. This collection of physical qubits acts together as a single, much more robust logical qubit. Some of these physical qubits are data qubits, holding the information, while others are ancillary qubits, acting as sentinels. Periodically, the ancillary qubits are used to check for errors in the data qubits through a process called syndrome measurement. They get entangled with the data qubits and are then measured. The result of this measurement, the error syndrome, tells you if an error has occurred, what type of error it was, and where it happened. Crucially, this is all done without ever directly measuring or disturbing the actual logical information you're trying to protect. Once you know the error, you can apply a corrective operation and fix it. The theory shows that as long as the error rate of the individual physical qubits is below a certain threshold, you can suppress errors almost completely. In 2023, a team at Google made a major breakthrough, demonstrating for the first time that this process actually works in practice, reducing errors in a real system. This was a critical step, proving that the quantum safety net is not just a theory. The combination of better qubit designs and powerful error correction leads us to the dawn of the next era, the age of the logical qubit. A logical qubit is the goal. It's a single unit of information encoded across many physical qubits, making it resilient to noise. This transition from fragile physical qubits to stable logical qubits marks the beginning of the end for the NISQ era and the start of true fault-tolerant quantum computing. The overhead, however, is staggering. Current estimates suggest that creating a single, highly stable logical qubit might require 1,000 or even tens of thousands of physical qubits. So while a company might announce a chip with over 1,000 physical qubits today, in a future fault-tolerant machine, that entire chip might be dedicated to creating just 1 or 2 logical qubits for computation. The rest would be working full-time on error correction. Getting to this point is the primary focus of the entire field. It means we need more qubits, better qubits, and less error-prone operations. The advent of functional logical qubits will be the watershed moment. It will finally allow quantum computers to perform the incredibly long and complex calculations needed to solve truly world-changing problems. So what kind of problems are we talking about? What happens when this fault-tolerant future arrives? In medicine and materials science, the impact will be revolutionary. We could precisely simulate the behavior of molecules. Imagine designing a new drug by watching exactly how it interacts with a protein in the body, atom by atom. This would massively accelerate drug discovery and lead to personalized medicine tailored to your unique biology. We could also design new materials from the ground up, like high-temperature superconductors that could enable lossless energy grids, or new catalysts for creating clean energy. In finance, quantum algorithms running on fault-tolerant machines could analyze vast, complex systems with countless variables to optimize investment portfolios, manage risk, and create financial models far beyond what we can currently imagine. This same optimization power could be applied to logistics, solving impossibly complex scheduling problems for global supply chains or airline routes. The intersection with artificial intelligence is another exciting frontier. Quantum machine learning could supercharge AI, allowing it to find patterns in enormous datasets at unimaginable speeds. This could lead to breakthroughs in everything from medical diagnostics to developing more powerful and capable AI systems. And of course, there's the famous or infamous application, cryptography. A fault-tolerant quantum computer running Shor's algorithm could break many of the encryption standards that protect our digital lives today, from bank accounts to government secrets. While this is a threat, it's also fueling the development of new, quantum-resistant encryption to keep our data safe in the future. The road to get there is long. It's a marathon, not a sprint, and the challenges are immense. First is scalability and quality. We don't just need millions of qubits. We need millions of high-quality, nearly identical qubits that can all be controlled perfectly. And we need to do this while maintaining extreme operating conditions, like temperatures colder than deep space. Second is the error correction overhead. The sheer number of physical qubits needed for one logical qubit is a massive bottleneck. We need to make our physical qubits better to reduce their natural error rate, which would in turn reduce the number of them needed for the safety net. The hardware itself is also incredibly complex. It's not just the quantum chip, but a massive system of control electronics, cryogenics, and lasers that all have to work in perfect harmony. As the systems get bigger, simply wiring and controlling everything becomes a nightmare. Despite these challenges, the progress is real and accelerating. Key milestones to watch for on this journey will be the first demonstration of a logical qubit that is provably better than its physical parts, and the moment we reach the break-even point, where our error correction code fixes more errors than it creates. The journey of quantum computing is taking us from a world where we work around noise to a world where we master it. The central theme of this next era is the end of neglect. We are moving from simply putting up with errors to building systems with resilience baked into their very design. The machines that emerge will redefine the boundaries of what is possible. While the challenges are great and the timeline is uncertain, the direction is clear. The future of computing isn't just quantum, it's resilient, and in that future, free from the tyranny of noise, the true power of the quantum realm will finally be unleashed.